Hello students, welcome to the IMS Academy. Now let's continue the smart revision on operating system part 2. In the part 1 we have seen 2-3 chapters like first introduction part and process management. In that IPC environment we have seen. So from deadlock onwards, deadlock and memory management and file system topics, we will try to revise with the important statement and necessary formulas which are required to be observed. Okay. So I hope you are audible, right? So kindly comment it. So if everything is fine, then we'll start the session now. Okay. So now from the IPC and synchronization part, the concepts we have seen like the various algorithms and where they are. So like satisfaction of like synchronization mechanism requirement like mutual exclusion, progression requirement and bounded weight requirement. We have seen some problems also we have seen. So apart from this, some more problem, 1 or 2 problem we will see from IPC environment, then we will continue for deadlock, fine. So now look at this question, another question. This question says, the below given 3 concurrent process used in the counting semaphore, what will be the initial value of counting semaphore ABC to always print? So gate 2022 and gate 24 and 23 should be printed. This is a order need to be printed. Now what are the values of ABC should be kept so that this order of printing can be done. So observe and tell me. So what is the answer for this question, all of you? So what values of ABC can be placed? Now look at this. So process P1, P2, P3 is there, right? So such type of questions we can predict it, like happen in so many year papers also. Like you see, the first they are saying that we have to print it what 2022. So 2020 printed by this process. So if P1, P2 concurrent environment nothing but ready queue can have process P1 and P2 and P3, all 3 present. It can be scheduled any one of them. So having one CPU, more than one process available in ready queue, it can be scheduled any one. But whatever the process schedule it, but P3 only should run printing, like others should get block. Now what must be the value should be there now? If B equal to 1, if I keep it, it will, so wait on means down on B nothing but its success it can print it. If A equal to 1 nothing it can print it. So B should be not printed, this should not be printed, like this should be first process should be. If P1, P2 tries should get block, only P3 should be available. So hence now I have to keep it what, which value? C equal to 1 if I keep it. So 1 down 0 successful, then it can print gate 22, then signal wake up is A becomes 1. So A becomes 1, B should be 0, then because I need 24 only. So where it becomes 1, now down on A equal to 1, 1 down is successful, it can print gate 24, then I am making B equal to 1. So B equal to 1, then I can run it. So definitely, so A should be 0, right, B should be 0 and C should be 1. This combination should be A equal 0, B equal 0, C equal to 1. Yes, the option 3 I should select so that this order of printing can happen. Yes, this type of question they can ask. So now such a way they keep it also. Sometimes the questions comes, I want to print what is the minimum value this code will print, maximum value the code will print, how many values can be printed, and now what is the order of semaphore operation I should place it so that deadlock will not cause and deadlock will cause. This type of questions definitely we can expect it. So this variety of question try to practice so that you will be in a good position to answer it. So we'll see another question. So P1, P2 two processes, assume that initial value of P and Q is 0 and 50 respectively and semaphore initialize x equal to 1. Wait and signals are up and down operations on x variable. What are the possible value of P that can take possible take when P1, P2 runs concurrently? So now P1, P2 two process here. Now PQ values are given and X value give also given. Now what they are question saying that what are the values can be printed? What are possible values PQ can be printed, they are asking. So how to solve such questions? How to solve? Now your semaphore value define how much? X equal to 1 only. So now look, these two cases can happen. So case number 1. So process P1 schedule then followed by process P2 can be scheduled. Case number 2, okay, case number 2, process P2 first, then P1 can be scheduled like this. Case number 1, if I run process P1 assumption, process P1 if I run it. Now one more thing need to be noticed, does it ensure the mutual exclusion or not? Does it ensure the mutual exclusion? Since semaphore value define x equal to 1, wait on, so we perform wait means what? Down operation. Down on 1 nothing but like 0 is successful, I can print it. If suppose if it is inside the critical section, if P2 tries x value already 0, so it won't enter. So nothing but is ensuring mutual exclusion. Any one of the process can start. After completion of one process only other process can execute, that is observation. Now case number 1, P1 x value 1, 1 down 0 successful, P equal to P plus 25. P value almost 0, 0 plus 25, P value will be 25 only. So P will be printed as 25. Now followed by P2 I am running, so process P2. So x value, now I am giving signal x, right? So signal on x nothing but x becomes 1. Now I will write down on x is success, now P equal to Q minus 10. So P equal to Q minus, Q minus 25, right? 25 only. So Q minus 30, Q minus 30. Okay, now see. So now P value initially 0, now Q value is 50, right? Q value is 50. Initially Q value 50. What operation? P equal to P plus 25. It is not touching what Q value, right? Now it is going to touch Q value almost 50. 50 minus 30 almost 20. So now P value going to update 20, right? So final value almost 20 will be there, right? Final value 20 will be there. If I run first process P2 will run P equal to Q minus 30. Q value is how much? 50 minus 30, right? 50 minus 30 how much? 20 only, 20. P value 20 is there when I run it. Now after that P1 will run, okay. So P1 will run, what is the P1? P equal to P plus 25. P value how much? 20 plus 25, this will be 45, right? So we have a possible values are 20 comma 25 only I will get it. 20 comma 25. I hope you understand all of you. See, so now, so P2 then P1, right? P2 then P1. P2 down, Q value is 50 minus 30, 20. Signal again run. Okay, P is updated here. P is only updated, right? So 20 plus 20, 45, that's it, correct. There is no other possibility. But what extension of question we can expect here? Understand? So now semaphore value x equal to 1, right? They can give 2. X equal to 2, they will give it. X equal to 2, they will ask what is the possible values of x? What is the possible values of what P will be printed, P will take when x equal to 2. When x equal to 2, what happens here? When x equal to 2, if P1 started executing, x equal to down on x equal to 1, enter the critical section. When process P1 in critical section, P2 also can enter the critical section. Because why? X equal to, when it is in critical section, x value 1, this also can try. Now, so inconsistency will create, so we will have multiple values. So such cases, how you can answer it? Understand? Enter the process P1. When it is updating, P value reading at 0, when reading 0 and updating to like 25, right? 25, first 25, P value 25, yes, 25. Then if preemption is occurred, if this process comes, Q value read, it will modify P. The modified value may be effect or not effect. So these are the observation you do. You might have practiced such things. Carefully write down the assembly level instructions. Assembly level instructions you write it and understand. You will get even different values also possible. This is another observation because 23 paper happened same way. They framed the same way they framed. So there are given two cases. When semaphore value 1, what is output? When semaphore value could define 2, what is output? This type of questions asked. Even other year paper also asked. So such type things need to be practiced. Fine. So these are the major observation from this chapter. Now moving into deadlock. In the deadlock, what are the topics you need to focus? That is very much important. All of you look this point. From the deadlock here, first of all, a definition we should understand. So definition and characteristics. Definition characteristics. What is a deadlock? Deadlock is a situation or a state. So it will occur when 4 necessary conditions are present. What are the 4 necessary conditions? One is a mutual exclusion should be present, and second one is hold and wait should be present. Third one is a circular wait should be there, and fourth one is a no preemption. Preemption is not occur. If 4 conditions are simultaneously present, that situation known to be deadlock. If there is a deadlock, these 4 conditions must be there here. If one of the condition is not present, there is no deadlock now. If one of the condition is not present, there is no deadlock. That's how simply you can observe it. That's only definition. That's only definition. Now, so when it comes to handling like deadlock, how we can handle it? Before that, we should also understand the definition of the resource allocation graph. Is like a graph having vertex and set of edges. Now, edges represents here, one is claim edge, request edge and assignment edge. The vertices represents here process end as well as resources. Circle will represent a process, a rectangle represents as a edge resources. Resource can be single instances, multiple instances, understand. So, this is a process, understand, this is a what resource. So, resource can have a single instance, nothing but if I specify one dot, single instances. More than one dot is there, multiple instances, nothing but multiple copies of a same resource type. What is the purpose of resource allocation graph? Resource allocation defines a state of the system. What is the current state? How many processes are there? How many resources are there? How many resource allocated process? How many are waiting? How many are holding? So, the complete picture of the system we can able to understand by looking at a resource allocation graph. This will help us to prevention time, even deadlock avoidance time, even recovery time also we can use this one. Okay. So, now, handling, deadlock handling strategies, if you see strategies, deadlock handling strategies. First one is the deadlock prevention. First one is the deadlock prevention. Deadlock prevention. The second one is the deadlock. So, deadlock avoidance. Avoidance. Deadlock avoidance. Third one is the deadlock. Deadlock. Deadlock detection. Deadlock detection and recovery. Deadlock detection, recovery. The fourth one is a deadlock ignorance method. Deadlock ignorance. Ignorance method. Deadlock ignorance method. So, these are the handling strategies, but the deadlock ignorance method, this is not any algorithm. We do not have any algorithm to do it this one. So, naturally most of the Windows and Linux operating system use this one. But from real time operating system, we can expect one of the 3 methods: deadlock prevention, deadlock avoidance, deadlock detection, recovery. Now, understand in this case, these 2 algorithms we understand here, deadlock will not occur at all. Under these 2 mechanisms, deadlock will not occur. But in this case, system will go to deadlock state, will detect, will apply the detection algorithm, will detect the presence of what are the process available, process are involved deadlock, then we recover it. That's how it will work. So, now look at deadlock prevention means what? One by one we will see. First one. So, look at the deadlock prevention. We have studied, but let's do the little brief revision on prevention. So, deadlock prevention. Okay, deadlock prevention. Prevention means what? You look at the necessary conditions. Necessary conditions for occurrence of the deadlock. One of the condition, at least one of the condition, if you dissatisfy, so deadlock will not arise. So, one of the necessary condition, one is what? Mutual exclusion. The second one is what? Hold and wait condition is there. Third one is what? No preemption condition, right? No preemption condition. And fourth one is what? Circular wait. Circular wait. Circular wait. Okay. Now, see mutual exclusion. So, one of the condition need to be dissatisfied. Either this or. So, straight away I can ruled out. So, mutual exclusion cannot be dissatisfied. Why? Because mutual exclusion dissatisfaction nothing but all shareable resources should be converted into non-shareable. That is impossible things. Resource access should be mutual exclusive. I cannot make it the separate copies. It should be shareable. Are you getting my point? So, mutual exclusion We cannot dissatisfy it straight away. I hope you understand why we are not able to dissatisfy. Because you see, accessing the printer should be mutual exclusion, right? Dissatisfied nothing but we have to allow more than one process to use a printer as a device simultaneously. That's not possible. Now, hold and wait condition. Hold and wait. So, dissatisfied nothing but you have to break this one. Hold or wait only. Either hold or wait. Do not do it same thing. Yes, we can able to now break it this one, breaking this one by giving two rules. You might have noticed also two important rules here. What are the two important rules? First rule is saying that before commencement of program execution, before starting of the program execution, take all required resources. Only hold the resource all. So, you are not waiting for anything. Middle you will not ask it. Beginning of the program, start of the program itself, you take the required resources. Only hold it. So, there is no point of waiting. So, yes, only holding is there. This one rule. Second rule is that you can make a new request in the middle. You can make a new request for the resources in the middle by releasing all the held resources here or holding resources. Again, I am saying that you release all of them, I make a new request. These two protocols definitely break the occurrence of the deadlock. It will prevent the deadlock here. Yes, I can use this condition for preventing the deadlock. But it is a restrictive algorithm. Why, sir? Because when I put these two protocols, there is two kind of problems can occur. One is resource may not be utilized properly. Other is starvation problem. Two problems arises here. Resource inefficient utilization, starvation. Because I said you can make a new request by releasing all. The moment you release the resources, operating system maybe take this resource assigned for other process. Now, when you make a new request of existing old and new resources, so an old resource may not be available. So, now process has to wait for get starvated to get the resources again, right. So, I hope you understand. And first protocol, as per the first protocol, hold all the resources. Some resource may not be required immediately to use, but still you are waiting, holding that, right, do holding. The other process who are required this kind of resources has to be starvated. But if you obey with the starvation, resource inefficient utilization, yes, it prevents the deadlock. That's a mechanism we apply here. So, no prevention, the third one. This also can be used, this also can be used, one of them. No preemption, simply allow the preemption to resource. Process should preempt the resource and given to other process. Other waiting process can use and release all of them. This process can be used later. Now, circular wait, this also one condition can be used to break the cycle. Yes, can be chosen for dissatisfying the condition. We can prevent the deadlock by using the circular wait. Breaking, you should make sure that allocation of resource should not form a cycle. Like this, we impose one rule called never allow a process to request a resource with a lower resource ID than the last one requested and allocated. Either increasing enumeration or decreasing enumeration process should be allowed to request for the resources with the IDs. Either one of them, then we won't form the cycle. If you are not able to form a cycle, definitely it won't occur the deadlock. That's how. So, one of three conditions, this is not possible, one of three conditions I can use preventing the deadlock. That's how I can run. I hope this is clear, all of you. Now, look at the second was deadlock avoidance. So, deadlock avoidance, okay, deadlock avoidance. How we do, we apply, there are certain algorithms. One is a resource allocation graph, I will use it, and second one is a bankers algorithm, So, bankers algorithm, I will use it, okay. Resource allocation graph, for all these single instance resource type, we can use the resource allocation graph to avoid the deadlock. Avoid the deadlock, understand, before allocation of the resources only, we run this some algorithms, then we will predict whether allocation of this resource will be leading to deadlock or not, unsafe. If it is leading to unsafe, we stop allocation. So, prior to this only we do this all the work, so that definitely deadlock will not occur. For single instances, suppose when you converting request edges to assignment edge, where carefully you should take care, request edge when you are converting assignment edge, you should not form a cycle. Such a way if you take care, then there is no formation of cycle, yes, deadlock will not occur. for the single instances. For multiple instances, Banker's algorithm will use it. Banker's algorithm, internally two algorithms are running. One is safety algorithm. Other is resource request algorithm. Both will be there now. What is the safety algorithm? So you know like what is the Banker's, why we use a Banker's algorithm. Before allocation of the resources, we run the safety algorithm, meaning if I allocate this certain of resources to this process, will my remaining system will be safe or not? If it is a safe, we start allocation. If it is leading to unsafe, if it is unsafe state, then unsafe state may lead to deadlock, we won't allocate that way. It will run the Banker's algorithm. Means it try to find a at least one safe sequence for the resources, then we can say the system is safe, so we can start allocation. No, we pretend that, yes, we do like we pretend that, yes, this resource allocated, like this we do, right? We have to pretend that resource allocated. Then if it is safe, then you start allocate. Otherwise, so do not allocate the resources. Are you getting my point? To implement this method properly, I need a prior information of the process request for the resources. Means every process must to declare their demand, how many resources required to complete this program. Based on the process demands and based on the available resource in the system, we are going to run the safety algorithm. If safety algorithm produce one of the safe sequence, we can say yes, the system is safe. Otherwise unsafe, unsafely to deadlock. That's how we do it. So now here no restriction. See, one of the theoretical question we can expect. Among these two protocol, deadlock prevention, deadlock avoidance, which is more restrictive? Deadlock prevention is more restrictive than deadlock avoidance. In this case, you can request, but requested value should be like requested process, like whatever the process request for the resource, whether able to grant it or not, again have to run the algorithm. Resource request algorithm means I have to pretend if I allocate it, if I get a safe sequence or not. If I get a safe sequence, yes, I can grant, otherwise we can straight away we can deny it. That's how it will work. And a gate point of view, they'll clearly give it process ID is demand of a process, current allocation they'll give it. We need to find a need vector available, then try to they can ask either safe or safe sequence, number of safe sequences. These types of questions we can expect, so that you try to practice the question, because previous year papers they have framed, and in this year also 2023 paper there was no question from deadlock. This year we can expect a question from the deadlock. I am hoping there would be 2 more questions from deadlock, that may possible from the Banker's algorithm only. Let's see what happens in 24 gate. Chalo. Now, so third one. So what is third one? Third one is what? Deadlock detection recovery. So deadlock detection, nothing but you understand. We allow the process to enter the deadlock. We apply the weight for graph, you might have studied, to detecting the processes, how many process resources involved in this one. Thereby we can apply the recovery algorithm. For multiple instances of a resource type, again I use the Banker's algorithm to be verify how many processes involved in deadlock. Thereby we can recover. Recovery will be very simple. We can kill the process, or simply kill one by one process, or we can do resource preemption. The resource preemption, you apply some cost effective mechanism, so that's why I can recover the you understand, from the deadlock state. This is all about deadlock. So two type of questions. One is Banker's algorithm based question. Other is, you understand, there is a question like which we can expect here, which you can expect. The last question: how many minimum number of resources should be allocated for n processes? Like they demanding D resource assumption, and so that deadlock will not occur. This is a simple formula which you can apply, where M is a minimum number of resource need to be apply, n number of process, D is a demand minus 1 extra you have to give it. Are you getting my point? Suppose process ID is there, okay, so there demand, maximum demand is there, maximum demand, and allocation is there, simple thing I will explain you, okay. Let's take process P1 and P2, they are demanding three resources. How many minimum number of resources should be there in the system? Deadlock will not occur. I said demand minus 1 you are looking at, demand minus 1, still all the process, most of the resources they got, because of one resource they can be in a deadlock or not. This is the state, you understand. They demanded 3, I given 2 copies. I given maximum resources, less than 1. Still all 3 processes can enter in deadlock state or not? Yes. So now total 6. If I give it 1 extra, this works extra copy, if I give it here, it will release 3, will release 3. So I can run it. So now 7 resources should be there now. That's why minimum number of resources should be given to the processes. So deadlock will not arise equal to n process. Their demand -1, give 1 extra 1 copy, give it. This is condition will not ensure the deadlock will not arise. Sometimes they ask question, to occur the deadlock, how many copies I should assign? 6 copies if you give it, deadlock will arise. Otherwise, sometimes they'll ask, I have this many resources, how many processes should run so that deadlock will occur, deadlock not occur. So similar way we can observe it. This type of questions also we can predict, and theoretical questions also we can predict from this topic. I hope you understand. So quickly we will move for the memory management. So memory management, what are the important topic need to be focused, we will observe it. So from memory management, all of you should understand some basics. Basic memory calculation type question they will ask. So some basics on memory calculations, first thing. Second one, you have to observe memory mechanisms we have now. So contiguous allocation, right? Contiguous allocation. Third one is what? So non-contiguous mechanisms. So non-contiguous mechanism. The fourth one is virtual memory. In that virtual memory, the paging concept is important. Like paging means, page replacement algorithms. Page replacement. So replacement algorithm. This is important thing to be observed. From the basics, what are the basics to be observed? So what is a memory? Memory you should visualize like a one-dimensional array of bytes or words. Array of bytes or words. Like I am saying, the elements, like array of this bytes or words, like you understand. Okay. So this is nothing but, you might have studied also, we can say set of, this all bytes, or it can be words, or it can be locations, or we can tell locations, or we can say cells also we can say. Now every location, this is a main memory, I am taking main memory. Okay. Every location or word byte is associated with the address. This is important thing to be noticed. Suppose this number of cells, number of bytes, number of words, if I define as a capital N assumption, and this address bits I am defining as a small n bits assumption, small n bits. Now length of this word or location, if I define as a m bits. So there is a relation between them. One is n, comma m, comma n, small n. Okay, relation. What is the relation? Capital N indicates total number of words. So that power of small n I can write it. Small n equal to log of number of words or number of bytes I can write it. So main memory size can be measured 2 power of small n into m bits, or n into m bits also we can measure it. M bits or bytes or bits we can express it. These are the important relations we can observe it. I hope you know this one, all of you. Okay. Number of words is power of address. Suppose example, there are 128 words are there. To address 128 words or 128 bytes are there in the memory. To address 128 locations, how many bits required? 7 bits required. 7. 2 power 7, well, how much? 128. That's what I written. 2 power 7, 128. So log of 128, 7 bits. Size will be number of words multiplied by word length. Like number of words multiplied by word length. There's a memory we can express it. This is, and also one should be very clear with like power values. 2 power 5 value how much, 2 power 9 how much, 2 power 11 how much, in terms of KBs, MBs, 2 power 29 how much, 2 power 21 megabytes, 2 power 25, 32 MB, 2 power 29 512 MB, 2 power 31 GB, 2 power 32 4 GB, 2 power 35 2 power 5 32 GB, 2 power 38 256 GB, 2 power 40 1 terabyte, 2 power 45 32 terabytes, petabytes, exabytes, zettabytes. This power value should know, so that during calculation time this is going to be help you a lot. This thing you have to be observed very, very clearly. Is it clear, all of you? Now coming into this contiguous memory allocation method. Contiguous memory allocation. There are two things we have. One is fixed partition. One is fixed partition method. Partition. Fixed partition method. Second one is the variable partition method. Variable partition method. Partition. Partition method. Okay. Now see, fixed and variable. This also we called multi-programmed with fixed number of tasks. This we called multi-programmed with variable number of tasks we called it. Under this mechanism, entire user area, especially under multi-program environment, user area further we are dividing in multiple parts to accommodate more processes, to improve the CPU utilization and increase the degree of multi-programming like this. If I use a fixed partition, nothing but you understand, user area is divided into equal or unequal sides fixed partitions, fixed parts will be there. Fixed parts you might have studied also. Now we have to see process request, we have to allocate a partition which is able to accommodate the requested process, that partition choose and allocate it. Sometimes situation occur, more than one partition can be able to accommodate a requested process. For this we have to use allocation policies. So what is the allocation policies if I study? First one, fixed, multi-programmed with fixed number of partitions. If you see the allocation policies. One is first fit, second one is the best fit, third one is the next fit, and fourth one is the worst fit, right? Yes or no? First free block is that is enough to accommodate, do it. Best available, best fit nothing but smallest hole, free hole you would find out, that is enough to accommodate the requested one. Next fit is similar like a first fit, but it won't scan from the beginning, it will start scanning from the next to the last allotment. Worst fit, the largest block we choose for allocation of the process. Like this differentiation you observe. Under fixed partition, in terms of space, best fit perform well. In terms of time, next fit will perform well. Now, some observations, important observation you have to do for fixed partition. So we have internal fragmentation, yes or no? Performances we see, first one, internal fragmentation will be there. Second one, external fragmentation, no external fragmentation in a fixed partition. Many times students confuse, fixed partition also will suffer from external fragmentation, but it won't suffer from external fragmentation. Why? Because partitions are not dynamic, right? Already fixed one. Are you getting? Partitions already fixed one, so we cannot get the external fragmentation. Now, degree of multi-program is limited here. You cannot increase the number of processes because it is number of processes equal to number of partitions only. Maximum process size you can say, maximum partition size only. These are the observations we can do for fixed partition. Similar with what? Variable partition. So second one is what? Multi-programmed with variable number of tasks. In this case, what happens here? In this case, we have to look at the process size, allocate the process, do the partition. Allocate the process, do the partition, hence no internal fragmentation. So there is a possibility of external fragmentation here. Yes, external fragmentation occurs. Means after dividing so much, there are some partitions here and there non-contiguously available, which is not going to be useful for like allocation of the process request. Variable partitions suffer from external fragmentation. Degree of multi-program is flexible, like maximum program size also flexible. Are you getting? No internal fragmentation. So these are the observations from variable partition. To solve this external fragmentation, we'll move for non-contiguous memory allocation. Under non-contiguous allocation methods, the first concept we should learn what? Simple paging, right? Simple paging. Second one is a segmentation. Second one is segmentation. Third one is even segmented paging also will be there. Segmented paging. Segmented paging. Like so even segmentation, there are many mechanisms, inverted paging, like hashed page table. There are many mechanisms which you apply for non-contiguous. Non-contiguous means what? Process we divide into parts like pages, and memory also divided into like frames. So this entire process will not be one place, we distributed over the memory. That is the meaning of non-contiguous. That is the meaning of non-contiguous. If you look at the simple paging, okay, simple paging, how we implement it? So program address space we call a logical address space, right? Program address space or logical address space, virtual address space. So or even we can say program address space also. We divided into pages, right? We divided into pages, right? Main memory also we divided into like pages only we called frames. So pages of a process we keep into frames here. Pages of a process we keep into frames. That is the observation we should do from simple paging. Okay. So now performance issues if you see, so like we in the classroom we might have studied also, right? Understanding how we have to divide the memory into frames, how to divide the program into pages, now how to translate logical to physical address, that should be clearly revised it. Okay. Now two things, the performance things if you see, performance of simple paging if you observe, two aspects you have to see. One is so time issues and other is what space, okay, space. So time nothing but what happens, because of this page table access time will increase, access time will increase, access time will increase. To reduce the access time we use our TLBs also, right? So I give an expression also, effective memory access time, in this case simple paging if I use it. So x into c plus c plus m plus 1 minus x into c plus 2m will be there, this expression, correct or not? This is a TLB access time, memory access time, x is the iterate of TLB. If TLB we maintain what, page number and frame number, corresponding frame number present, we get the physical address, one memory access we can get it. If page table is like TLB miss occur, so TLB access time plus page table access time plus memory, both should do accepted. So hence we require 2m, and even to improvise we can add the cache memory for that expression also given, so that you can observe to place it. Space is just nothing but here, no, page table, like a page table overhead plus internal fragmentation overhead will be there, right? To reduce this one we use a concept of like optimal page size as well as multi-level paging. Important things all of you. You should revise and work out on the multi-level paging. So like here finding the optimal page size, that also proven, and multi-level paging need to be applied regarding from this one. So the space issues can be solved here. That's about simple paging. This need to be covered. Here two types of question comes, time based and memory based question comes. So try to solve enough problems in this so that you are able to answer it. Fine. Now look at this next concept, we will see the virtual segmentation. So segmentation, what you have to study from segmentation, we won't do fixed equal sized pages, unequal size parts we divide, memory also unequal size we divide it. Now unequal size chunks nothing but segments we stored it in non-contiguous manner in the memory. So like a paging we need segment table which required to translate from logical to physical address. So that part you might have studied, but majority questions was not there in segmentation, as a concept you can learn from there. So most important next one will be what? So you should be focused virtual memory, very important thing. What virtual memory concept says that? Virtual memory concept says that, so under normal if a virtual memory concept is not there, if you apply the paging concept as a non-contiguous mechanism, if I want to run a process having n pages, you should find n empty frames in a main memory, all pages, entire program you should load and run it. Virtual memory is not a memory, please understand, it is not a memory, it is a concept. It suggests that do not require to load entire program into main memory, only required pages you load it and run, and runtime only you can fetch from secondary memory. So that is the concept of virtual memory, so that it can increase what degree of multi-programming more, throughput also will increase, more number of processes we can keep it, because the entire program is not going to execute at some time, and all the program is not required to compute at the same time also, right? That is the reason we keep many of them in secondary memory, runtime only can fetch it. Okay. So Here runtime, what when you start runtime fetching, page may not be available. We call page fault. When page is fault, again we have to runtime fetch from the secondary memory, allocate it. So that part you should be focused more on here. You understand? I given one expression, effective memory access time by using demand paging, virtual memory concept implemented by demand paging. That's I given. If there is a page fault, service time required. No page fault is there, 1 M is required. This important formula. 2019 paper, there was a question on this one, or even 21 or 22 paper, there was a question here. Okay, what the question? They splitted when page fault occur. Again, what we do? We will bring a page from secondary memory. I want to place it. Memory is not there, full frames are full. You have to apply replacement algorithm, right? You have to apply replacement algorithm. When you apply replacement algorithm to remove one page, understand what happens? The page can be modified, dirty, non-dirty. Dirty cases means you have to write back. If dirty is not there, simply load it. Like this consideration they will give it. This page fault rate something. If page fault occur, this much time is required. Page fault not occur, this much time will occur. Thus parameter in terms of percentage they will mention. So properly substitute, you will get the answer, ma'am. That is one important thing you have to observe from virtual memory. Now from this point, so now as I mentioned, right, when page fault is occur, we have to bring a page from secondary memory, you have to place into main memory. When memory is full, so we have to remove one of the frame. Which one you have to remove? So that is based on the replacement policies. There are various replacement policies. One is first in, first out. Second one is the least recently used. Third one is optimal, and fourth one is the MRU. Like fifth one is what, like least frequent count, and most counting algorithm, most frequent count. Like LRU approximation also there, LRU approximation. So like second chance algorithm, enhanced second chance. There are various replacement policies are there. You should understand. Even last year 2023 paper, there was no question properly applying, like how many page faults, what is the hit ratio, those questions did not ask. Again we may expect a question from this area. All of you from either CO or OS point of view, page replacement or block replacement algorithm bound to come. So try to revise these topics. FIFO, how it will work, LRU, optimal, MRU, right? So this if you done, then yes. So now from this, what you can say, memory management part you can be able to address. So I hope it is clear now. So coming into the point, file system from last topic. Some important topics I will say which you need to be focused more on. So file system means what? From operating system point of view, if you see, the visible part, like visible part of the operating system if you observe. So now suppose somebody asked where is the operating system means what? The visible part of the operating system is what? File system only, ma'am. Okay. Purpose of file system is to store your data on secondary memory devices. It is completely abstracting the physical properties of the secondary memories, hard disk. Then it is creating environment where I can write it. From GATE exam point of view, 2-3 topics will important here. 2-3. So from GATE exam point of view, 2-3 topics are important. See, so like thrashing is there, like thrashing, see. So like just I am focusing more on GATE point of view. So there was no any question from thrashing. Thrashing is the situation, you understand, where high paging activity is there, more disk activity is more, and CPU utilization comes down, degree of multi-programming is more, keep on loading more processes. This situation is called as a thrashing. Are you getting? Lot of page faults occur, further pages need to be serviced, and other side have whatever ready queue being empty, long term schedule keep on increasing the pages, keep on increasing the process here, CPU utilization comes down, disk utilization very high. This state is what thrashing. Reasons are lack of memory, high degree of multi-programming, maybe reason as one of the page replacement algorithm also, maybe page structures also, like storage environment also, page size also. There are many things which will cause occurrence of a thrashing, but primary reasons are lack of main memory frames and high degree of multi-programming. High page fault rate will lead you to thrashing situation. from this topic file system. So try to focus understanding the inode structure. So inode structure you should be revised properly, and so disk space allocation method, disk space allocation method, disk space allocation methods, disk space allocation methods, disk space allocation method. So can you tell me what are the disk space allocation methods we have? One is contiguous allocation, right? Contiguous allocation. Second one is what? Non-contiguous, nothing but linked allocation. Third one is what? Indexed allocation. It should be revised, and also observe their like performances. Performances nothing but you want to see. So with this like causing the internal fragmentation, external fragmentation, type of access supports. So whether increasing the file size possible, those properties will be there. You should revise this one topic, and other topic is disk scheduling algorithm. Disk scheduling algorithms, right? Disk scheduling algorithms. One is first come first serve. Second one is a shortest seek time first. Third one is a scan algorithm, and fourth one is a look algorithm, and fifth C scan. This C scan, and sixth one is a C look. Okay. So this look at all working principles. This is much important topic from this file system. The rest is fine only, because so majority time questions are asked on inode structure, asking the file size, right? Giving like there are 8 direct address pointers and one single indirect and one you understand double indirect, triple indirect. They are giving the block size or pointer sizes. They'll ask 2 types of question we can expect. What is the maximum file size with this respect to inode system, and what is the maximum file size with respect to disk also. So disk is given, you have to see the disk block address, number of disk blocks, multiply, you will get the disk size. That's how you have to work out here. And you see this in this case they will ask what is the seeks, number of seeks or number of seeks time. So total time required to perform this number of requests. That type of question comes here. These are the things need to be observed from this one. So overall what I am trying to say, see ma, like no detailed things I am not discussing, like just in this course, like this session is going to be only helpful for those already revised 1 or 2 times. And quickly we are looking at the what topics are there and how topics are important for the gate, okay, and how they are working, like our working nothing but some important factors about each topic which we observed from these last 2 sections. So first session we focused on introductions, process management, IPC. Then in this case deadlock and memory management, this part we observed. In the similar way upcoming, like understand this 27th we planned for 3 hours, I planned for computer architecture also. So try to join for computer architecture, where will take even little more time to be observe all the things now. Okay. So now overall, so high priority topics from this like operating systems, if you observe it, first majorly focus on CPU scheduling algorithms, IPC synchronization, deadlock, the specially bankers algorithm, from memory management, paging, multi-level paging, and virtual memory, that is page replacement algorithm. From file system you focus disk space allocation method, theoretical point, high node structure as a numerical questions, and numerical questions of disk scheduling algorithm. These are the essential topics from operating system. So I hope you understand this session, definitely useful. Last moment revision quickly within one hour you can revise by watching this video and try to join for this even computer architecture. So upcoming session, that is 27th January. So like you can check for the timings. So okay ma, we'll see for the COA next class. Thank you so much.